One question we've got to answer before we deal with file systems is a file. What is a file? The way I would describe it is probably it's some named collection of, let's say, related information stored in secondary storage. Stored in secondary storage, so that way it's going to survive. When your process terminates, it'll still be there. When the system reboots, it'll still be there, unlike, let's say, normal RAM. It's what we think of as long-term storage. Now, there are exceptions to this, certainly. One that comes to mind, for instance, is the Palm Pilot, which was one of the first personal digital assistants, PDAs. So a precursor, let's say, to an iPhone. And so there, all of the data was actually stored in dynamic memory. It just wasn't cleared when a process quit. And on a reboot, that actually dynamic RAM still was maintained. You may say, well, what happened when you had to replace the batteries? And the answer, and by the way, this was, I think it ran on 1 or 2 AAA batteries. It would last for about a month. So it was very low power usage. And what happened was actually when you pulled out the batteries, there was still enough charge in a supercapacitor to be able to replace those batteries. In any case, this is kind of weird. It was permanent storage. It's just it was a little precarious permanent storage because if your batteries ever came out, you really only had 30 seconds to replace them. The Unix and Windows model is one where a file is just a collection of bytes. So this is Unix, Windows, and I'll say also current Mac OS. Okay, so in this case, the file is just a single collection. And when I say collection, I really mean sequence of bytes. So a binary, like an ELF file, is a sequence of bytes. A text file is a sequence of bytes. This is not always the case. So other possibilities, well, certainly more extravagant possibilities might be you might have a file as a database. So that has been done in some non-mainstream OSs. So the Apple Newton had an OS where you had defined records and the OS knew about what the keys were on those, and you defined indexes for those keys. And then you could go ahead and look things up, like find all the records where the age is greater than 19 and the country is United States, for example. In the Palm OS that I described earlier, it was a much simpler, not really database, just array kept in memory for each application of chunks of memory. Unlike normal memory, though, as I mentioned, these were permanent storage, so these were not deleted when the process was closed. And then you would just kind of look through this array to find the records that you were looking for. The fact that this is all in memory meant this went very fast. The OS itself was aware of a couple of attributes of each record, a unique ID, something called a category, something to see whether it was deleted or not, or whether it had been modified. And it used that for syncing to a desktop machine. Then we've also got intermediate things. Let's look at many OSs have had the idea that text files are different from binary files. So text files are, instead of a raw sequence of bytes that happen to have new lines in it, instead sequences of lines. So we'd have line 1, line 2, up to some line n. And then you navigate through the file line at a time. And the operating system is aware of that. So one advantage is you're not actually having to worry about what are the delimiters between lines. So it is a carriage return, is it a line feed, is it a carriage return line feed? That can all be fairly confusing. There are also operating systems that have more than a single stream of data. And these basically allow multiple streams. So we can look at this, for instance, in Mac OS, classic Mac OS, let's say. we had a data fork, which was the traditional sequence of bytes, and then also a resource fork, which was a little mini database of resources. Okay. This could be used, for instance, an application. The executable was in the data fork, and the resource fork had all of the user interface information, the contents of menus, dialogues, what the text were for buttons, where the buttons were laid out, and so on. And what this meant is that you could take an application, open up a resource editor for the resource fork, and change, for example, an application from English to German without actually affecting the code of the application itself. That was very handy. A simpler example of how you might use this is you might have a text file, like a C file that had all of the C code in the data fork, and the resource fork could contain, let's say, the last time you printed this C file, did you choose to do 1-up or 2-up or double-sided, and it would contain that last settings that were used for printing this file. Today, NTFS on Windows and HFS Plus on Mac both do support still multiple streams. Okay? But the fact is that it's not really used that much. And the big reason is it's very hard to transfer files, right? It's confusing to try and transfer to a Unix file a file that actually has two forks of information. One thing we should discuss about a file is not just this collection of related information, or in Unix or Windows really just this, or Mac these days, just this single sequence of bytes. But as well, let's talk about metadata. So the metadata of a file is information that is not the contents of the file itself. So that includes the name. It also includes things like its size. Let's talk now about file metadata. So metadata is really all the information about the file that isn't the contents of the file itself. So that would include things like, what's the name of the file? I guess you could say maybe the size of the file too. But certainly if there were some max size of the file, that would be part of the metadata. We might have permissions about the file. We might keep track of who owns it. What group does it belong to? What other things? When was it created? When was it last accessed or modified? Other information might be like an icon, whether it's hidden or locked. Okay. If we look at something like Unix, so for example, we do have the name, the size. We have permissions, which are based on the owner and the group. So for Unix, we actually have three sets of permissions. We have permissions for the owner, we have permissions for the group, and then we have permissions for anybody else. And those permissions are in the form of permissions to read, to write, or to execute. So each of these is a bit that can be on and off. And it's common to express these in octal. So for example, if you are creating a file, you can provide these permissions. And similarly, on the command line, you can use changed, which changes these permissions of a file. So if I have a file foo.txt, I want to make it so I can read and write it, but the group and the world can only read it. So in that case, I would do basically a 6, which would be the read and write bits, a 4. So 644, changed 644, foo.txt would change it so that this file was readable, writable by me, and only readable by other people. If it was an executable file, I might instead choose it to be 755. 755, so it's read, write, execute for me, read, execute, and read, execute for others. In Unix, we do have creation date, last access date, last modified date. We don't have hidden, so if you want a hidden file, that's done by convention. And the convention is you have the file name start with a dot, and then ls knows not to display it unless you put in a special flag. Other metadata have included in classic OS, for instance, there was a type and a creator. So the type was the type of the file that specified, for instance, that it was a text file or that it was a Microsoft Word file, a document file, or it was a spreadsheet file, and so on. And the creator said who created. That is, when you open this file, who should open. So for a text file, it kind of matters a lot. Let's say you are a programmer, and so you might have a foo.c file. And your foo.c file you want to open up in your C compiler. Well, sorry, you don't want to open in your C compiler, you want to open up in your CIDE. So maybe you want to open that up in, what would I use? TextMate, for example, might open that. So in that case, the type would be text, but the creator would be TextMate. On the other hand, some other text file I have might have a totally different creator. This is not used much anymore. It turns out that's not really, it was very useful, but not very useful for compatibility with other systems. So what is used almost universally is file extensions. In the past, that used to be on DOS, very specific in that you had 3-character extensions. That's more generalized these days. So now the .c is the extension. So we could have .c, .doc, .docx, .txt, all those sorts of things. On Unix, this is a convention. In some cases, it's sort of enforced by the OS. There are a lot of binary files, though, that don't have a particular extension, and those are often distinguished via a magic number. So, for example, files that begin, if you have an ELF file, for example, it begins with, so these 4 bytes are always at the beginning of an ELF file. So you can, if you're given an ELF file, verify or doesn't completely verify that it is an ELF file if it has this, but if it doesn't have this at the beginning, then you know for sure it's not an ELF file. There are a bunch of magic numbers for a bunch of different files. It's not that there's any central repository exactly for this. Everyone just sort of makes up their own. But they are all documented. At the man page for Magic, you'll see where this documentation is, and you can see basically a long database. Many file systems support the concept of links. So on links, there are 2 basic kinds. Symbolic link. And in a symbolic link, let's say we have over here the contents of bar. Okay, so this is the file bar, and there's the contents of bar. And then we could have a file foo, and the contents of the file foo are a pointer to bar. So what does this mean? Well, this means a couple things. First, when you try to access foo, it's going to have to hit 2 files. It's going to first look at the contents of foo, find basically the reference to bar, and then go to bar. Can you have multiple symbolic links in a chain? Yes, you can, although there is a limit as to how long that chain can be. You certainly wouldn't want to have loops. There's no check in the operating system for loops explicitly, but at some point, I think it's about 8, it figures, oh, I must be in a loop because this is crazy that I would have that many symbolic links, and so you get an error. Right? The problem with this symbolic link is if you delete bar, foo still is there, and it's only when you try to access it that you get an error. These links can cross volumes. So if you have, one disk here and another disk here, you can have a symbolic link that crosses. Like all of this. The alternative is what's called a hard link. So in this case, foo and bar are actually referring to the exact same contents. So we have our contents here. And then we can have foo that refers to this, and bar that refers to this. And there's no idea of which one is the real link to the contents. They are both 100% links to the contents. Now, one thing that the file system has to do there is make sure that when you delete a file, like let's say you delete foo, that it doesn't actually delete the contents. So there has to be somewhere a count to see how many links there are to this contents. One thing to note is that although a symbolic link can cross volume boundaries, a hard link cannot. So we cannot do this with a hard link. Okay? Because of the fact that we have to have this sort of reference from name to content, and that only works within a particular file system, not across file systems. And that's what this really is, multiple file systems on different volumes. One attribute of file systems is the namespaces. So original file systems had a single namespace. All right, this is, for instance, original IBM PC floppy drives. You had a single namespace and you had files in here. So you might have a.text, and b.doc, and so on. But you could not have two files named a.text. That wasn't possible. Another possibility, not so common these days, would be, let's say, two levels, one per user. So user Joe might have his own namespace, and user Sally might have her own namespace as well. And so they could each have files named a.text. Today, if we look, for instance, at iOS, the applications have their own namespace. So between different applications, they can't collide. But what's most common is a hierarchy, where we might have a root, and then from the root, we have various subdirectories, let's say user and home and bin. And then within bin, we might have files like cat and move, etc. But that I would still be okay if I had user roads. I could have my own cat in the roads directory if I wanted, because the namespace is this hierarchy. And so only within a specific directory only within a specific directory are you limited to not repeating file names. Let's talk about some common operations that you can do on files. All right, so what can we do? Well, we can certainly create a file, delete a file, open, close, read, write. Seek to move to a particular location within a file. We can maybe get and set attributes. Things like whether it's hidden, what the permissions are, and so on. Let's look at one of these. Let's look, for instance, at open. So at open, we're going to actually look at the file permissions. And when I say we, I mean the operating system. So the operating system is going to look and say, okay, what user is trying to do this open? What are the permissions for this file? Do they match? Can I go ahead and do the open? The open is going to take a parameter, whether you're trying to read or trying to write, so it can keep track of that. And then from then on, you can seek in the file, you can close on the file, and you'll be able to either read and or write depending on how these permissions have been opened. But it's not going to look at the file permissions anymore. It'll just, once you do an open, it will keep track of, can you read, did you request reading or writing? Do you have permissions for reading or writing? If the permissions don't match, you'll get an error. If they do match, then it will keep in this open file table information about whether we are able to read or write. In creation and deletion, we also need to look at permissions, right? We shouldn't just be able to create anywhere we want. So on Knuth, you can't create in /, for example. How is that determined? Well, if we're creating, it can't really be an attribute of the file you're trying to create. Instead, we look at permissions of the directory. So write permission on a directory means that you can create and delete contents of that directory. The readable means you can iterate through and see the contents of the directory, and execute means you can actually execute or access a file in a directory. So if you don't have read-write permissions, but you do have execute permissions on a file or on a directory, you can actually open a file in that directory as long as you know the name, but you can't iterate through to try and find the name. The less common operations, right? So other operations, we might have an append, we might have a rename. As far as Unix is concerned, append is actually an attribute of open. So when you open the file, you say, I'd like to open it in append mode, and then anything you write automatically goes to the end of the file. Rename, Unix doesn't have. How exactly does a rename work, right? What happens when you do move A, B? Okay, so you want to rename A to B. What are the system calls that happen? Right, we've got a file. Here are the contents. It's named A. Well, what we do is we actually we link and unlink. So perhaps I should put on here a common operation of link and unlink. So delete on Unix is actually unlink. And on Unix, we also have a link command. So we would actually link A and B. So now all of a sudden, we have A and B referring to the same contents. And then we would unlink A, and now it's no longer referring to it. That's why if you try and move contents across file systems, you get an error. Move says I can't do that because it can't link across the file systems. Instead, it's up to you to do a copy and then a delete. Let's look now at directory operations. Okay, and we can again break them down into common. Like, let's say create and delete. We can open a directory, close a directory, read a directory. And then less common might be renaming, linking, unlinking. It's interesting to note that in Unix, these are not system calls. These are actually libraries. And the reason for that is in Unix, directories are actually implemented as files with pointers to their contents. We'll see that in just a little bit later. So let's look at an abstraction of the disk. Basically, we can just view the disk, and we will, in a later lecture, come up with a better model. But for now, let's just look at it as a sequence of blocks. So from block 0 all the way to block n-1. Commonly, a block might be 512 bytes or 1024 bytes. And then the only operations we have are read, block I, and write, block I. And let's look now at file system metadata. So that's different from file metadata. Let's say we've got the disk. All right, and we've got, let's say, contents of file 1. And these really need not be contiguous. That may be separate parts, separate blocks in the disk drive. We might have the contents of file 2. And then what I'm going to say is everything outside of that is the file system metadata. So what is that? Everything outside of that? Well, that'd be which blocks are free. That is certainly some metadata we need to keep track of. Which blocks are free, which blocks are in use. Which blocks are used and in what order because that order pretty much matters, of which file. So we want to know that, for instance, file 2 has these certain blocks in this particular order. As well, the directory structure and all of the file metadata as well I'm going to consider as part of the file system metadata, like, again, the names, the attributes of the file, permissions, and so on. For the file system, we've also got to keep track of which files are open. So we're going to have a system-wide open file table. So what's that going to contain? Well, we'll contain, for instance, the attributes, a count of how many file descriptors actually have this file open, because we don't really want to completely close the file until the last reference to the file is closed. We might have the current location within the file, the access mode, so that we can know whether to allow reads or writes, and etc. And notice that the same file can be open and present in this open file table more than once. So what's an example? Well, let's say I open a file with read access and I open again with write access. Then I've got two different open file table entries. Or actually, if you just open a file more than once, you're going to get separate open file table entries. Then we also have a per process open file table, right? Those are basically indexed by the file descriptor. Some of these can share. So we could, for instance, have a process which has a file descriptor, let's say 0, that references this particular file. And really, what this would be is a reference to, so this would be the process file descriptor table. And then we'd have a system open file table. So this would actually reference here, some entry in there, and then this would point to the file contents. Now, is it possible a particular process could have multiple file descriptors referring to the same file? Sure. If I do a dupe, that's exactly what it does. If I do, let's say, a dupe of 0 and I have no other files open, then now that's what I get. And the ref count gets incremented here. I can also actually have it shared, right? I can have a separate process, and its file descriptor 1 may also point to this file table. How? Well, at some point in the past, basically we have to have had a shared file descriptor that got duplicated. So if this is a child and this is a parent, that could happen. Or if we had a common grandparent that these both were children of, the common grandparent opens a file, gets a file descriptor, then forks and creates these children. Those children can now go ahead and use that file descriptor, including duping it, and they'll all be sharing it. At some point, you need to find the blocks of a file. There are several different ways you can do this. So one way you can do it is you could just have all the blocks in a file contiguous, on the disk. So they're all adjacent. That's great. That means that the accessing the file is very fast. So if we just looked at our abstraction of the disk, then we might have, for example, file 1 spans these blocks, entirely contiguous. And then file 2 might be following that, and file 3, so on. The advantages of that is extremely fast because as you are reading successive blocks of the file, you can do that at full speed without having to do any seeking on the disk. We'll talk about that in a future lecture. The disadvantage is we have to know the size, or at least the maximum size of the file when we first create it. And that's normally not the case. However, this does work great for immutable media that can't be changed. So this is great, for instance, for a CD-ROM or a DVD-ROM, right? So as we are building up the CD, building up that file system, we just read each file, find out how big it is, allocate that much contiguous space, read the next file, allocate it, and so on. That works great. If any of you have ever used a defragmenter, on Windows or Mac, what that is basically doing is reading a file, reading all the blocks that may be different locations on the disk, and finding its size, and now going and creating a new file that is contiguous and copying over the data. So when you end up, all of your files are contiguous, and then it's quicker to access for the reasons I described below. So this is one way, contiguous. A second way would be using a linked list. So the idea here is we have some blocks. Let's say that our file has 3 blocks. And let's say this is block 4 and block 7 and block 1. And so this is the first part. So this is the files block 0, files block 1, and the files block 2. And what we do is just reserve a little space in the block for the number of the next block. So this one would be 7. 7 points to, let's say, 1, and 1 points to -1, right? Something like that. So that works. We don't have any external fragmentation anyway. There are 2 major problems. So one, it's slow to get block in. To get to block in, if you're starting at block 0, requires n disk accesses. So that can be very slow. So order n disk accesses. Well, n disk accesses. Second problem is in our block, our data is no longer a power of 2, right? This might be 512 minus 4 or 8, depending on how big this pointer is. And that can just be difficult. It's just more common to have things be a power of 2. Another possibility, let's say we had this same arrangement where we wanted to have this file having its 3 blocks, block 0, block 1, and block 2, and they were at these locations 4, 7, 1. What we would do is we would basically get rid of this pointer. So we go ahead and use the full block size for the contents, and then keep an external list. And this would just be indexed by block number. And the contents would be the next block number for the file. So we would have 0, 1, 2, 3, 4, 5, 6, 7. Let's say this is a very small disk. And so we would have some reference that this file starts at 4. Okay, so we would have a reference to 4. 4 would then say its next block is at block 7. 7 would say its next block is at block 1, and 1 would say its next block is at -1. It would be important that this list not only be in memory. So we want it to be in memory, and then we could also store it on disk. So we'd have to have it on disk so that we could figure out where the 4 files, which are the blocks that are associated with that file. But in memory would make it very fast. Then if we wanted to find, let's say, the nth block of this file, we just go in memory and go n steps, memory steps though, and then we have a single disk accesses. And since the disk access is what's so expensive, basically we're still order 1 in the number of disk accesses. Let's just do a little calculation. Let's say with a 20 gigabyte disk. Let's say our block size is 1K. So that means we have 20 gig divided by 1K, so that'd be 20 megabytes of blocks. All right. And then that would mean we'd need, let's say, a table size of around 80 megabytes. One thing that's also done, so we looked at this idea of just contiguous, and this is completely discontiguous, we could kind of combine those. So we could say, for instance, gee, I am writing to a file, and rather than just blindly getting a random block, I'm going to try and start writing at the beginning of a chunk of blocks. So I might say, I'm going to take blocks 4, 5, and 6 and write to those. So we have basically combinations of contiguous blocks and discontiguous blocks. These contiguous blocks let's call them subsets, sort of the entire file, are called extents. And basically, it's just a starting block number and a length. Another approach that we can use for finding the blocks of the file was introduced by Unix. So this is what's used by x86 and was used for quite a while in Linux and so on, but that have changed over time somewhat. So we introduced the concept of an inode. So the idea is we are going to go ahead and allocate one block. This is the inode block. We're going to have some attributes in it. And then we're going to have a sequence of block numbers. And how many do we have? We have, I think it's 10. That's 10 here. Let's just make it 11 for good measure. Okay. It's basically whatever amount of space is left after we have the attributes that we need. And what we do then is we just go ahead and put block numbers in here. Right? So this represents the contents of a file. So the contents of a file is going to be, so attributes are some metadata about it. One of the attributes, in fact, will be the size. So that's how many bytes it's going to be. And then we'll have block numbers. So this might be 4, 7, 1, using the same example from last time. So we've got 3 blocks in this file. The size tells us exactly how many bytes because the last block may not be full. And that's great, except what's our maximum file size? Well, if this is 11 big, we can basically be the maximum size is 11 times 512, right? 11 times the block size. So, you know, this is around 6K. Well, I don't know about you, I've seen a lot of files bigger than 6K. What we can do then is look at, let's say, these blocks. And see that we've got our 3 blocks associated with it. And we can continue down here and do all the blocks. So the workaround that we do is we say, I know, let's go ahead and make one of these blocks an indirect block. So we're going to have, let's say, 52 here. And right, this is 4 and 7 and 1. And this is the first block of the contents of the file, the second block of the contents of the file, the third block of the contents of the file. And then we get to the 10th block, and then we go ahead and we say, okay, this one is going to point to a block, and it's going to be an indirect block. That is, it's going to be a bunch of pointers to direct blocks. So like so. So we'll go ahead and have a bunch here. So now all of a sudden, our max size is bigger. So with one indirect block, with no indirect blocks, we have 11 times 512, which is around 6K. With one indirect block, Well, now we have 10 times 512 because we turned one of these direct ones into an indirect, so we lose one there. But then we add in how many blocks can we fill up in an indirect block. And that's just going to be 512 divided by 4, or 128, right? So this is, yeah, really the way we want to think of it is we have 138 blocks we can refer to, and that times 512. So this is what, more like, let's say, 60K? So better, but there's still a lot of files that are bigger than that. And so the solution is, well, if one indirect block is good, we could have more indirect blocks, and that'd be fine, but it'd still only increase this linear. So instead, what we're going to do is we're going to say, okay, let's take the second to the last to be a singly indirect block, and we'll make the third from the last be a doubly indirect block. So this will be, let's say, 64. 64 goes up here. 64 is going to be a double indirect, and it points to singly indirect, and then these each point themselves to individual direct blocks. All right, so in this case, what's the total number with 2 indirect blocks? We have 9 direct blocks, right, that we get to directly. And then we decided this was 128 indirect. And then plus 128 squared, doubly indirect. Okay, so what's this going to be? 128 squared, that's 2 to the 9th. So that's 2 to the 18th. So this is around 2 to the 18th times 512. 512 is 2 to the 9th. So 2 to the 27th, right, which is about 1 gig is 2 to the 30th. So 512, 256, 128 megabytes. That's pretty good, although, as I'll say again, I have certainly seen files bigger than that. And so the solution that Unix uses is we actually have triply indirect as well. So the triply indirect basically has 3 levels of indirection. We have a triply indirect block that points to a bunch of doubly indirect blocks. Those point to a bunch of singly indirect blocks, and those then point to the final ones. And so for 3 indirect blocks, and I don't really want to say with 3 indirect blocks, what I really mean here is with triply indirect blocks. So we have 1 single, 1 double, and 1 triple. Then it's going to be basically 9 plus 128 plus 128 squared plus 128 cubed, all that times 512. And so this again is going to be about 2 to the 7th, 2 to the 21. Looks like this calculation was actually incorrect. So 128 squared, 128 is 2 to the 7th, and for some reason I had it 2 to the 9th. So this is 2 to the 14th times 9, which is about 2 to the 23, which is 8 megabytes. If we go in here with a 3 indirect, we have 2 to the 21 times 2 to the 9. So we can support up to 1 gigabyte files. And of course, if we use 1K blocks instead of 512K blocks, then these numbers are a lot larger. So we can support much larger files. So what's the advantage of this approach? Well, there's a couple. One, small files just take a single disk access. So this inode is going to be stored in memory. We have a small file. We basically know if we're within, the first 5K of it, that we can just find directly what block number it's at and go read that block number. So that's good like for .h files and things like that, for which we have a whole lot of them. So we want to be able to get to those quickly. And then for the largest possible file, the worst we have to do is find the triple indirect block, read the triple indirect block, that's 1, read the associated double indirect block, that's 2, read the single indirect block, that's 1, and then read our final block, and that's our final. So we have 4 disk blocks we have to get to instead of possibly 1. Note there is caching going on, so if we're accessing the same location roughly in the same file, all these indirect blocks are also going to be cached in memory, so we won't have to pay the price of going to the disk for those. By the way, one of the exercises that you're going to do is add doubly indirect blocks to XV6. So currently XV6 just has a single indirect block. So it has the direct blocks and a single indirect. You're going to go ahead and modify it to add a doubly indirect. One thing that the file system needs to do is keep track of free space. So how's it going to keep track of free space? There's really 2 basic approaches that can be done. One is to have a linked list. So have a linked list of block that points to block, that points to block, that points to block. So what you could do is, instead of putting inside a block just one linked list to a free block, you could put a bunch of free ones so that it kind of fans out. So you could have, for instance, a particular block number here, which is the head of our free list. And then we could say like 3 is free, 5 is free, 32 is free, 1 is free, and then 8 is next. And then we'd have another block, which is 8, and so this is conceptually a pointer to here, and then we go and do that. So one advantage of this is we don't need much memory, right? We can just go ahead and store, let's say, this first block in memory. The cons are we can require disk access in order to allocate. So if we use up 3 and 5 and 32 and 1, then we're going to have to go and read 8. A common thing that's done is to actually have a bitmap. Okay, so we have a big bitmap. And that's in memory, and it's also on disk. Okay, it's on disk because when we shut down the machine, it's really important that we come back up again. We know what blocks are free, and we don't really want to somehow search through every block in the disk to try and figure out whether it's free or not. So we have 1 bit per disk block, and what we would do, for instance, if these are, let's say, 32 bits here, this would tell us the status of block 0. And the next bit would tell us the status of block 1, and this would tell us the status of block 31. In any particular entry in here, right, let's say this is the ith entry, and this is the jth bit, that would tell us about block I times 32 plus j. So all we've really got to know in order to, let's say, mark a block as free or not free is take the block number, do this arithmetic, do a little bit manipulation, and figure out where we are in here. It's easy to allocate contiguous blocks. We can look for runs of 1s. One problem is it can be slow to allocate if the disk is close to full. Because we've got to search through here to try and find a non-zero. Now, one good thing is we don't actually have to search through looking bit by bit. We can actually just look at the entire word, right, and say, is it non-zero? If it's non-zero, one of the 1 bits is set, and we can go in and find it. So we can go through at least 32 at a time rather than individual bits at a time. Let's say we have 16 gigabyte drive, and we have 1K blocks. Right, then that means we have 16 megabytes of blocks. And then if we divide by 8, that will be 2 megabytes of free bitmap. I'm dividing by 8 just to look at the number of bytes. If I want to go ahead and divide by 32 here, that'd be fine, but then I'm going to multiply back by 4. So that's the same as just dividing by 8. So this free list is really important to keep track of because it's going to be pretty common to want to go ahead and either put a block in the free list. For instance, we've unlinked a file, or we might need to allocate a block from the free list. For instance, we're writing past the end of a file into a new block. Let's look now at how Unix implements directories. The basic idea of a directory is, so a directory is a file. So we have a bunch of rows where we've got the name, we've got the attributes, and then we've got the contents. So a name might be, let's say, a.out. An attribute might be 755, for readable, writable, executable. And then the contents might be inode, 63. And we can have several of those, one for every file in that directory. So let's look at what happens if we try to access, for instance, user include standard.io.h. Okay. Well, the first thing to know is that root has a special inode. So inode 2 is the root inode. That's the inode for slash. So what's the inode look like? Well, we know the inode has some attributes, and then it's got lists of block numbers for the contents. So let's say that the block number is 52. So this is the slash contents. So we'll have a 2 here. And then let's look at the contents of inode 2. Well, we're going to have some different contents. I'm going to assume we have 4 here. Our contents are going to be the name dot, and the location is going to be inode 2. Dot dot is going to be inode 2. We're going to have, let's say, user is inode 5, and what else do we have in slash? Bin is inode 63. So 2 is a pointer down to here. Before we look at user, let's look at this dot and dot dot. When you are in a shell and you say cd space dot dot, the shell doesn't interpret that any differently from any other directory. So dot dot is actually a directory in every directory. So every directory has both a dot and a dot dot. The dot points to itself, that is its own inode, and the dot dot points to its parent inode, except for the root, where dot dot points back to the root. So that's an interesting idea where we don't need special knowledge of what dot and dot dot are. We just need to set up the file system appropriately. User is going to be inode 5, so we're going to go look at inode 5. We again have, and so this is slash user. And we again have attributes. Let's say user is not a very big directory, and so we only have a single block number here. So we're going to have, 16. Okay. So this is going to be a pointer to block 16, and that is the slash user contents. It's a directory, so we know we have a dot, and we have a dot dot. Dot points to itself, so that's back to inode 5. Dot dot points to its parent, so that is going to be 2. And then we've got some other contents. Let's say there's include, And there's also a /user/bin. So we'll have that one as well. So that user bin is 101 and include is 75. Let's look at inode 75. So again, this is /user /include inode. And here, again, we have some attributes. The attributes include, for instance, how many references, how many links there are to this inode. And here, now we're going to look at the block. So this is 19, which points down to here. We know we have a dot. We know we have a dot. Dot points to 75, which is itself. Dot points to the parent /user, which is up, over, and down. And among other things in here, the most important one we have is standard AO.h. So standard AO.h, let's say, is inode 99. We look over at inode 99. We have some attributes. 99 points to here. And now we have the actual data blocks. So let's say we have a 25 here. Then this is block 25. And this is the first block of /user /include /standard AO.h. And of course, there may be multiple blocks as well. So this is how directories are organized with respect to inodes in Unix. And so the way to have multiple links is just to have multiple references in particular directories. So either in different directories or in the same directory with different names that point to the same inode. And the number of pointers to the inode is the link count in the inode. When the link count goes to 0, then the inode can be removed, as can all of the blocks that it refers to. Let's talk about how links are actually implemented. So in a hard link, we would have different directories, or really different directory entries, pointing to the same inode. So this directory might be calling this foo, and as a reference this inode. This directory might be calling it bar, and has a reference to the same inode. Within the inode, we'd have a ref count of 2. And of course, this ref count needs to be maintained on disk, right? Because whether we're running or not running, still this inode has 2 directory entries pointing to it. We could just as well have also baz here, let's say, and share it as well. For symbolic links, it's in some way simpler. A symbolic link is just a file. So if I do a symbolic link and I link foo to ... /bar. Okay, then what would happen? Then we have a directory, and within here we have foo. Okay, we also have a ... which points up to the parent's inode. So this points up here, and the inode has attributes and has a pointer down to a block, right? And within here, we assume we have a bar, right? And we have now an inode number for bar. And then we have some blocks that actually point to the actual data. Foo would point to its own inode, right? All directory entries point to an inode. So let's point to an inode. Let's put it up here. So we have an inode. And here it's going to have course attributes, and it's going to have a single disk block. Let's say this is 59. So disk blocks are going to be in pink. So there's a disk block here, and there's a disk block here, and there'll be more for bar. For foo, its disk block's going to be here, and its contents are very simple. That string, ... /bar. So a symbolic link can be relative or it can be absolute. In this case, it's a relative one. So it's always going to just go up to ... and then find bar, and that's the direction we can go to. If bar isn't available, we'll get an error when we try and open that symbolic link. If we try and remove foo, it's going to go ahead and remove the directory entry here, and it'll go ahead and remove this inode. This inode had a ref count of 1, so when it goes down to 0, this goes away, and then its block goes away. If, on the other hand, we're over here and we remove foo, then the ref count is going to go down to 1, and we lose our directory entry here. If we then remove baz, the ref count goes down to 1, and we lose this directory entry here. But we still have this reference here, and only when we remove bar, we remove this directory entry, the ref count goes to 0, we lose the inode, and then we also lose, of course, the blocks of the file. I was going to say the blocks of foo or the blocks of bar, but we really don't know the name of it. It depends on kind of how you look at it. So when the ref count goes to 0, we lose the inode, and we go ahead and free up all the blocks that it refers to.